Good afternoon. This last video for Chapter 11 will be dedicated to the notion of elastic and inelastic collisions. The best way to understand this concept might be just to watch some videos. When you hear the word elastic, you may think of a rubber band or some other stretchy object, some object that can be deformed and then have its original shape regained after you remove the force which caused it to stretch. And that's no coincidence because many of the types of materials involved in elastic collisions have that elastic behavior. So case in point, here's a rubber ball which is about to bounce off of the floor. Observe how, on the way down, this ball has a certain quantity of kinetic energy. And for a brief moment, that kinetic energy appears to be gone because this thing slows down and even comes to a stop. Right there, see, it was barely moving, or really it wasn't even moving. The center of mass was not moving for just a moment. So you can ask yourself, where did all that kinetic energy go? Well, wherever it went, it seems to have come right back because the ball bounces upwards. Now, it's not going back up as fast as it was on the way in. It slowed down a little bit, but it's almost as if that kinetic energy was stored somehow and then returned after the bounce. And of course, you can model this thing like a spring. See how it squishes? It takes work to squish that ball. If you did that in the palm of your hand, you'd have to squeeze pretty hard. So it's not the traditional spring that you conceptualize when you're taking physics classes. It's not a piece of metal that's been wound into a helix shape, but it's springy nonetheless. And you can think of all that kinetic energy as temporarily being stored in the intramolecular, or should I say intermolecular bonds, of all those particles within the ball. So the energy gets transformed from kinetic to potential and then back again to kinetic. And that's a characteristic of an elastic material. I think there's another similar video coming up after this. Same idea. This is a harder looking ball, so I would expect it to keep more of its kinetic energy. Yeah, the upward bounce is almost as fast as the downward bounce. So an elastic collision could be thought of as one involving elastic materials, which allow any kinetic energy to temporarily be transformed into potential energy within the material and then returned as kinetic. Now here's another example of a distinctly non-elastic, or we say inelastic collision.
Oh! Oh! That, well, it just landed in the car.
It's parked in the car. It's just parked in it.
Look at this camera shake. Oh, like a giant. Whoa! That, well, it just landed in the car.
It's parked in the car. It's just parked in it.
You know what? That hit the ground so hard, it shook the camera. Look at this camera shake. Oh, like a giant. Whoa.
So it's pretty evident that the very large quantity of kinetic energy brought in by that wrecking ball was lost and not recovered. It didn't bounce back up at a speed comparable to the speed at which it came in, and it didn't send other stuff flying off at that speed. So there's a definite loss of kinetic energy. Sure, there's some debris being kicked out from the sides of the vehicle, but there's no way that that debris is carrying away the same energy that the ball brought in. So where did all that energy go? Because it's got to go somewhere. Well, you can imagine that some of it was dissipated as thermal energy. Most definitely the zone of that car right underneath the wrecking ball has got to be a little warmer. And also, it's deformed the material. It takes energy to squish metal. If you were to take an aluminum can in your hand and crush it as hard as you could, the work that you did, where is it now? It's different from if you were to take a baseball and throw it. When you throw a ball, you can see the energy. It's associated with the motion of the ball. It's kinetic energy. But when you crush that can, where did that energy go? Well, I imagine it's been dissipated thermally in the process of deforming the material. And that's what we're looking at here. So this is definitely an inelastic collision. Now, in neither of these previous, or in neither this example nor the previous example, could we make any statement about momentum being conserved. Let's look at this example right here. If we define the system as the car and the ball, we really cannot make the assertion that the momentum of that system is conserved, because as they're colliding, as they're interacting, there is a very large force from outside the system, and that would be the ground pushing up on the tires. And that force is significant because it's got to counteract the impact force, if you want to call it that, from the wrecking ball. So this is certainly not an example where we would want to assert that momentum is conserved. But I've got a couple other videos where we can maybe make that approximation. I'll have to thank the slow-mo guys once again for providing pertinent materials for our curriculum here.
And an injured the next time we try it. Right.
All right, I think I'm ready.
Okay. 3, 2, 1, go!
Keep an eye on the K-rail.
This is great.
He's booking. He's booking.
Come on. Come on, come on, come on. Oh! Oh! Weight of the K-rail is too similar to...
We are going to watch that again in slow-mo, but as you watch this at regular speed, think about the momentum carried in by each vehicle. One of the vehicles is going to the right, one is going to the left. And depending on how you set up your axes, that would mean one car has a positive value of momentum and one has a negative value. And if those cars have the same mass and the same speed, you can see how the total momentum would be basically zero. So if the two cars crash together and come to a stop and end up with zero momentum, that's zero before, zero and after, you could make the case that momentum is conserved.
To the two cars being pulled, which meant that the timing was off because it got yanked away. So this time we've doubled the K-rail. This time?
Well, do it again. So, let's see what happens.
Maybe we'd be even more tanned and injured the next time we try it. Right.
All right, I think I'm ready.
Okay. 3, 2, 1, go!
I think I'll play this a little bit slower here. So there we go. Playback speed. Let's go with half speed.
On the K-rail.
This is great!
He's booking. He's booking.
Come on! Come on, come on, come on. Oh!
So I think it would be fair to say that momentum in this collision is more or less conserved. Again, you had positive momentum brought in by the white car, negative momentum brought in by the other car. If the masses are comparable and the speeds are comparable, just calculate MV, you'd find equal and opposite quantities add up. Zero momentum before, zero momentum after. Now, yes, there are forces from outside. If your system is the white car plus this other car, the largest forces present would be the contact forces between them. Those are internal forces. There is some friction between the dirt and the tires, but it's probably rather insignificant compared to that very large contact force. I believe that's called the impulse approximation. In that approximation, you ignore outside forces if the contact forces are much larger. So this is an example of momentum being conserved, but kinetic energy not being conserved. It's very obvious that the kinetic energy has been dissipated. Each car brought in a large amount of kinetic energy. Now there's none left. Where did all that energy go? Well, it took a lot of energy to deform these materials. They're probably warmer now. And also we heard the collision. And sound waves, although they don't carry a whole lot of energy, they do carry away energy. So vibrations, waves, that's going to sap some of the energy of the system as well. This would definitely be a non-elastic, or as we say, inelastic collision. Let's watch it.
Oh! Oh my God! Oh! Look at the steam escaping from there. That was class. It was like the front of the car's burst. Did you see that?
That was a lot of debris in the air there. I can't wait to see that back.
That went like 20 feet. That was amazing.
That is not bad. That is almost dead on.
Oh, the wheel moves on the left-hand side one. Look, the back wheels.
So you can see some of the kinetic energy winds up in the kinetic energy of these flying pieces of debris. But again, that really can't be very much because those are small pieces. I think the bulk of the energy will be dissipated thermally.
Look at that melon coming out.
So the back car, look at how high off the ground the right-hand side car is. It's just taken off.
That's great.
And for the last example, here's some typical lab equipment. We actually have this sort of stuff in our stockroom. Here are two carts on wheels with presumably low friction bearings so that we can ignore the effect of rolling friction. And these pegs on the front ends of the carts, they're attached to springs. And remember the video just a moment ago of the rubber ball that was squished, and I asserted that the kinetic energy was being stored in those intermolecular springs, so to speak. Well, the same idea applies here. The incoming kinetic energy of these carts should be very briefly stored as potential energy in these springs. You can't see the springs, they're just inside the cart. So let's watch this one-dimensional collision between two masses, which is approximately elastic. An elastic collision is one in which whatever kinetic energy was there before the collision is still present after the collision.
Times the mass. Each one of these blocks is the same mass as this guy. So this guy has 3 times the mass. I'll send this guy in with some speed v, and we'll see what happens.
Okay, that was quick.
So this guy has 3.
Observe that these two carts, they did not come to a stop the way the two vehicles did in the slow motion video. Both cars are moving afterwards. And if you were to calculate 1/2 mv squared for both carts before and after, you would likely find that the total kinetic energy after is close to the initial kinetic energy. There's going to be some loss of energy as these pegs knock up against each other, but much less of a loss than we saw with the slow motion collision between the cars.
Times the mass.
Let me do this a little slower. Just make a casual observation of the speeds before and after.
I'll send this guy in with some speed v, and we'll see what happens.
Now, if you wanted to approximate even better an elastic collision, you'd probably want to mount very strong magnets, like some of those neodymium magnets on the front, and then you could be confident that they wouldn't even touch each other as long as you didn't push them too quickly. They would interact electromagnetically and repel before they ever made any contact. So there wouldn't be any loss of energy to sound or thermal dissipation upon impact. So that's the best, perhaps the best example I can think of for a macroscopic elastic collision. Now, as soon as you get down to the microscopic domain, it's easier to imagine elastic collisions. How about two protons launched at each other? You guys know that protons repel each other, and you can imagine that two protons might approach each other and stop before even touching because of their mutual repulsion, and then go their separate ways. And so it's almost as if they never collided at all. Another example, let me pull up a simulation. I've used this example recently, but I'll show it to you again. This is a gravity simulator. You've got something like a star, a planet, let's call it Jupiter, and then a satellite launched from the Earth. And that satellite is going to get a gravity assist from Jupiter. So a few seconds into the simulation, you'll see this thing. After having orbited the sun, it'll draw near to the planet and get launched by the gravitational attraction of the planet. So train your eye on the turquoise ball here. And here it comes right there, or right here. That would be another example of a collision. I'll replay that. So a collision doesn't have to involve repulsive forces the way most collisions that we're familiar with do. It could also be an attractive collision. As long as there's some exchange of momentum and kinetic energy between the two objects, I would say that counts as a collision. So let's look at the math now. There's really one very special type of collision that's analyzed in your chapter. And the conditions seem a little restrictive, but it turns out that you can generalize it to some other related scenarios. But you need to be familiar with the formulas that predict the outcome of this very specific type of collision. I'll just call this the special collision that we're talking about. It needs to be one-dimensional. it needs to be a two-body problem. We're not looking at a collision between 5 or 6 objects, just 2. And one body is at rest initially. That's important. It doesn't matter which one, but one of your masses needs to be sitting there initially. And lastly, actually, there's 2 more conditions. One of the conditions is that it's an isolated collision. And by that, I mean that the external force on the system is 0. Think of those 2 vehicles crashing head on. Yes, there's outside air drag and friction, but those forces were small compared to the collisions between, compared to the forces between the vehicles. So we just approximate the external forces being 0. Remember what you can conclude from this? Apply Newton's second law in this form to the whole system. If there's no outside force, remember this is external, then there's no time derivative. In other words, the momentum's not changing. The momentum is conserved. And lastly, here's the more stringent condition. It has to be an elastic collision. In other words, whatever kinetic energy is there present or initially must still be there after the collision. Every one of these must be satisfied if you're going to use the following equations. Okay, we're going to enforce 2 conservation principles. And I really shouldn't use the phrase conservation principle for kinetic energy because we don't really think of kinetic energy as conserved quantity. It may be the same before and after for a particular collision, but there's no conservation principle. So I'll try to avoid that word for kinetic energy. Okay, we need a little picture here. Here comes mass A at speed VA. I'll use the number 1. So the letters distinguish the masses and the numbers distinguish the times. Let's say here's a second mass. And remember, one of the conditions is that one of the bodies is at rest initially. So I will let this one be the one at rest. VB at time 1 is 0. And after these collide, well, I'm just going to use some common sense here. If this thing really is more massive than that, then this thing's probably going to keep going. Maybe it just slows down a little bit. So I'll draw a shorter arrow and call this VA2. That's the velocity of mass A at time 2. And maybe mass B kind of got launched off to the side with some velocity VB2. And one way of phrasing the problem would be to state the masses and the initial velocity of mass A. We don't need the initial velocity of mass B because we know it's 0. If these were the quantities you were given, well then what would be the quantities you're interested in finding? I didn't specify either of the final velocities. So find VA2 and VB2. And the remarkable thing is that this can be done every time. We don't need to know what type of materials these objects are made out of. It doesn't matter what the shape of this thing is or what its speed is. If we know that these conditions are satisfied, then the outcome of this collision is determined every time, which is pretty cool and not at all obvious from just F equals ma or even from common sense. But the math puts a constraint on the possible outcome. So let's apply those constraints. The first one being that the total momentum before the collision has to be the total momentum after. Well, since this one's not moving initially, its momentum at time 1 is 0, and we only have to worry about the momentum of mass A. Now afterwards, they might both be moving, even in different directions, so we need to account for both momenta after. And let me point out again that I'm making a small abuse of notation here. The convention that we usually follow is if the quantity can be negative, we need to recognize that it's the component of a vector. So I really ought to have a subscript x here or y to indicate that this is the component of a vector and that it can be negative. But I don't want to get bogged down with the subscripts. I'd rather get bogged down in this explanation about my notation. It's understood that 1 or both of these quantities could be negative. They are vector quantities. Okay, well, if we were given both masses and the incoming speed of mass A, then how many unknowns do we have in this equation? We know that, we know this, we know this, we do not know this, and we do not know this. So this equation has, how about I underline them, 2 unknowns. You can't solve one equation for 2 unknowns. So if we have any hope of determining the final velocities, we're going to need a second relation. Where does that come in? That's the whole point of making this specification. In an elastic collision, the kinetic energy at the end is also the same as the kinetic energy at the beginning. So I want to make it clear that you cannot always apply this equation. It's not always applicable. So for the 2 vehicles that you watched crash head-on, you definitely cannot apply this condition because most of the kinetic energy was lost. It has to be an elastic collision. Here is the incoming kinetic energy of mass 1. Mass 2 has no kinetic energy because it's just sitting there. And afterwards, we've got 2 quantities that we need to calculate the kinetic energy. And I'm going to underline the same 2 unknowns. And there it is. Now we have 2 equations in the same 2 unknowns. That's an algebra problem we should be able to solve for those 2 unknowns. Now, if you had actual numbers to deal with, if you knew the mass of these billiard balls, for instance, you could plug those masses in and solve this math problem with actual numbers. You could do that uniquely for any problem that you encounter. But wouldn't it be nice if you could solve this algebraically ahead of time and have explicit formulas for VA1 and VB2? Because then you wouldn't have to do the algebra every time. You could just derive the formulas once and never do it again and plug in the numbers. And that's what I'm going to do. You see, I did this algebra, I don't know, maybe 10 years ago. I'm pretty sure I did it. I don't feel the need to do it again, certainly not for this video. You can do it if you want to, but I'm going to quote the results, and you should have these on your note card. You should know when you can apply them. You want to be able to recognize a scenario in which these are applicable. What is that scenario? It's got to be a one-dimensional collision, so you can't have like the cue ball hit the 8 ball and then they both go off in some V shape. That's no good. It's got to be a one-dimensional collision. One of them had to be at rest initially. And you might be asking, okay, how many collisions do we actually look at where one of the objects is at rest? You know, car crashes often, that's not the case. They're both moving. Of course, a car crash is not elastic anyway. But here's why this condition is actually not that restrictive. If you've got a collision between 2 objects, both of which are moving, even if they're moving at different speeds, you can always put yourself in a reference frame where one of them appears to not be moving. For instance, what if you have a car going at 40 miles an hour this way and another going 50 miles an hour that way? Imagine yourself in a golf cart going 40 miles an hour with this car. You can't go 40 miles an hour in a golf cart. Okay, you're in some other vehicle and you're moving along with the first car so that in your frame of reference, that car is not moving. Now you've got a car coming in even faster, smashing into something that's at rest. So you could put yourself in that frame of reference and then use the equations we're about to develop. And then at the end, take your results and transform them back to the original reference frame, the reference frame of the ground. Now, we're not going to do that because we really don't have time, but just be aware that that's why these equations are not as restrictive as you might think. Okay, so I'm going to say solve for VA2 and VB2. Let's skip all the algebra. Here's the result. In your book, I believe we'll use different notation. You want to be flexible. The velocity of mass A after the collision. Here it is. Are you ready? It's difference over sum. Mass A comes first, minus mass B over MA plus B, times, well, it's got to be in terms of mass A's original velocity. It can't depend at all on mass B's original velocity because we know that that velocity is 0. So there it is. That's how I remember it. Difference over sum times the incoming velocity of mass A. What is B doing after the collision? If you did the algebra, you would find the same denominator, different numerator. Also times VA1. And there they are. Notice there's no ambiguity here at all. The outcome is determined. Not obvious, but the fundamental law from which all of this comes is F equals ma. So if you follow everything we've done this semester, we're postulating that you should be able to predict the outcome of a two-body, one-dimensional elastic collision with no outside forces. You should be able to predict that outcome precisely because every piece of matter within the system is interacting via this dynamical law F equals ma. And the ability to correctly predict collisions using this formula would serve as, I don't know if that's the right way to put it, but it's evidence in support of the correctness of Newton's theory of mechanics. Okay. Usually what I do during the semester is explore some of the obvious cases here, but I'll just make this brief. In fact, let me see if I can pull up a collision between two billiard balls. Okay, even better, actually, I found a nice physics demo. Let's try to predict what the two, if we're colliding two carts, what they're going to do if the two carts have equal mass. So if they both have the same mass, there's no point in distinguishing MA from MB. Let's just call them both M. And then we would have M minus M, that's the numerator of 0, suggesting that the incoming cart would have a velocity of 0 after the collision. In other words, it would just stop. Down here, we've got 2m over m plus m. Well, m plus m is 2m, so 2m over 2m is 1. And that says that the second cart after the collision would have the same speed as the first cart before the collision. In other words, they're just going to, quote, exchange velocities. So let's take a look at a video of that. You've probably seen this guy before. So here's two cars, very little friction from outside, so we can argue that momentum is conserved. And I believe these do have magnets mounted inside them, so we can model the collision as elastic because they're not really going to bang against each other. They will repel from a distance. And that's exactly the type of collision we're talking about. So watch what happens with these equal mass carts where one of them is at rest before the collision.
After the collision. So what you can see is that the hit.
He's going to do the same thing in reverse.
And we can do the same thing in reverse. It transfers.
As predicted. In fact, while we're at it, let's go ahead and look at one or two other limiting cases. What if you've got a, let's see here, something like a bowling ball. Imagine you're out in space where there's no gravity, so you don't have to worry about that complication. There's just a bowling ball flying through space in a straight line, and it's about to strike a very small but hard rubber ball. So I'll call this big M and little m. So this is mass A, this is mass B. This one is just sitting there before the collision. What's going to happen to these two? Well, your common sense will probably tell you what's going to happen. This one will barely slow down at all. If it's, you know, a 15-pound bowling ball and this is just a few grams, why would this thing slow down? So it's basically going to continue on at the same speed. This one is going to get launched forward, and we know that it has to go faster than the bowling ball is going, because if it was going the same speed, they would be moving together. But your common sense tells you if this is a rubber ball, it's going to get bounced forward. So there it is. This speed should be unchanged. This speed will be positive and greater than this speed. The question is, how much greater? Well, according to our equations, the velocity of mass A after the collision, remember I'm calling this mass big M, the other one is little m, big M plus little m. Okay, now let's pick some numbers again. Let's go with SI units or just any system of units, it doesn't matter. What if this is 1,000 and this is like 0.001? 1,000 plus 0.001. Can't we just ignore the 0.001s compared to the 1,000s? So this is basically big M over big M, which is 1. As expected, the velocity of this mass is barely changed at all. Now what about the second guy, the little bouncy rubber ball? 2 times big M over big M plus little m. Just like before, if this is 1,000 and this is 1,000th, let's just ignore it. And then we've got 2m over m, which is just 2. So not only does the bouncy ball get launched forward faster than the bowling ball was already going, specifically it gets launched at double the speed. None of that is surprising. Let's look at another one. What about if the large bowling ball was the stationary one? By the way, why did I pick a bouncy rubber ball? Because this has to be an elastic collision if you're going to use these equations. That's one of the restrictions. It can't be a collision between two things that dent easily. They've got to be bouncy, springy, elastic materials. Okay, here comes little m this time with velocity VA1. So mass A is now the little guy, mass B is the big guy. And let's apply our equations here. So what will the little one be doing after the collision? Well, this time mass A is the little one. So it's little m minus big M over little m plus big M. As before, if this is 0.001 and this is 1,000, these are negligible. And we've got negative big M over big M, which is just negative 1. What does that tell us? It tells us that the little bouncy ball is just going to get launched backwards with essentially the same speed that it had coming in. Not surprising, right? Now, with a bowling ball and a rubber ball, you wouldn't expect it to be that pronounced. I think this thing is going to start to move a little bit, and this probably won't bounce back at exactly the same speed. And one reason being, even a rubber ball is not perfectly elastic. What about the second mass afterwards? Remember, MA is now the little one. So the velocity of the big one after the collision would be 2 times little m over little m plus big M. And once again, if this is 0.001 and this is 1,000, you're looking at a fraction like 2 millionths, 0.00002, which is practically 0. So as expected, this one barely moves at all. It's nice to see that these formulas predict a result that we would expect anyway, based on our common experience, or common sense. And you know, this one you're particularly familiar with. What if you are playing outside as a kid or whatever, and you drop a rubber ball towards the floor? Now, you probably know that most rubber balls, when dropped, collide with the ground, and then they bounce back up, but they don't go as fast as they were going when they hit the floor, usually. So those rubber balls you can buy from like the gumball machines outside of a grocery store, I don't know if they still do that. It seems kind of unhygienic. But suppose that ball is going 5 miles an hour when it hits the floor. It's probably going to bounce back up at something like 4.5 miles per hour, if you're lucky. And that's because the rubber from which those balls are made is not 100% elastic. As the ball gets squished when it collides with the floor, some of that kinetic energy is not going to return. It's going to be dissipated thermally. It's hard to manufacture, I would imagine, or design or develop a truly elastic material. Now, I do have here something called the Super Ball, which my father bequeathed to me. He had this in the late 1950s. And I don't think they make these anymore because they're really darn elastic. They bounce off a hard surface almost at the same speed. So I'm sure a whole bunch of kids were playing with these back in the day. You throw it against a wall as hard as you can, and it comes right back at almost the same speed. So that would be rather dangerous. If you know of a place to buy these, maybe you could pass that along to me. Super balls. Okay. Where were we? All right. How can we relate this collision between the hard rubber ball and the earth with what we were talking about just a moment ago? Where's the picture I drew? There we go. Can we relate it to this particular collision? I think we can, because, hey, isn't this planet Earth? And this is the bouncing rubber ball. Of course, you're dropping it from the surface, and this is not to scale, but this really is a collision between a much more massive object, the Earth, and a teensy-weensy object. The Earth's mass is essentially infinite compared to the mass of the rubber ball. So let's see if we can, it's not even really worth writing down, is it? Because we've already done the work. Let's call this mass of the Earth. So I'll put subscript Earth, and then I'll just leave the mass of the ball as little m. Yeah, the math is telling us right here that the ball would bounce straight backwards with the same speed it had originally. So the speed after is the same as the speed before. The only difference in the velocity is the minus sign. Again, actual rubber balls don't do that because they're not 100% elastic. So there's one little bit of terminology you should be aware of. If a collision is inelastic, it simply means that the kinetic energy after is not equal to the kinetic energy before. In fact, it's going to be, in most cases, less. If it were more, that would mean you had some sort of explosive that introduced energy into the system, or a loaded spring. So I'll put usually. Now, this is not universal terminology, but most books reserve this term, perfectly inelastic, for a specific case in which the final velocity of the two masses, the final velocities, are equal. In other words, the two objects that are colliding, they have to stick together and move as one. And then you could just call that final velocity v2. You would not even need the subscripts a and b. So that's how your book does it. A lot of other books do the same thing. They reserve the term perfectly inelastic for when the two masses stick together. And I keep forgetting to go back and prove this to myself, but I believe, at least in one dimension, that you suffer the greatest loss of kinetic energy for a perfectly inelastic collision. Don't quote me on that, but I believe that's the relevant result. Now, you may also see the term perfectly elastic. Your book doesn't use that, but you can imagine what that would mean. Elastic in general means that you recoup some of your kinetic energy. So a perfectly elastic collision would be one in which all the kinetic energy is recovered. So some books might use this or apply that label to this scenario. They would call that perfectly elastic. I believe your book does not do that. They just call it elastic. So I will go with that. If all the kinetic energy is there at the end, we just call it elastic. If you lose kinetic energy, in fact, if you lose kinetic energy and your two masses are stuck together, that's perfectly inelastic, right? Just think of the bouncing rubber ball, the stretchy rubber bands. Stuff that stretches and regains its original shape is elastic. Let's use these results now to solve a problem which was not in your homework, but it's at the end of the chapter. This is number 63 from chapter 11. A smaller mass of 20 grams is fired to the right, where it strikes a larger 100-gram ball, which is just hanging from a string. And after this ball rebounds, we're told that the larger ball swings upward to a maximum angle of 50 degrees before coming to rest momentarily and then swinging back down. And we're supposed to figure out how fast each of these was moving just after the collision. So this is a lot like the ballistic pendulum. Allow me to label some times here. Since they've already used the subscript 0 here, I'll say T0 is just before, and I'm going to call it the elastic collision because we're actually told in the problem that the collision is elastic. So think of these as two hard rubber balls. They certainly would not be two chunks of clay. That would not be an elastic collision. Actually, we're supposed to find V naught. Yeah. So based on also the length here is 1 meter. That's from the pivot, where the string pivots, to the center of this ball. Based on that distance, this maximum angle, and the masses, we're supposed to figure out just how fast this thing was going. Well, remember, the equations that we just developed for a one-dimensional elastic collision, which is isolated, those will relate the final velocities of the two masses which are colliding to the initial velocity of the one mass that was moving before the collision. So there's a relation between those three quantities, those three velocities. I think what we can do is use the maximum height attained by this one to figure out how fast this one was going. And once we know how fast this one was going, we should be able to figure out how fast this one was going. T1 will be just after the collision, but before, I'll call it the upswing. So before the larger masses had time to swing upwards and come to a stop before falling back down. And T2 will be at the top of the swing. And just like with the ballistic pendulum, as this ball is making its way up, so when the ball is right here, its instantaneous velocity, I should say, is that way. The tension would be perpendicular, so there's no work done by the tension. The only work done here is the work done by gravity. That's a conservative force, so we can argue that mechanical energy is conserved. So I'm just going to use capital E, not E sub mech. I'll say that the total mechanical energy at time 2, when it's at the top, has to be the same as the energy at time 1 when it's at the bottom of the swing. Let's go ahead and put the origin at the bottommost point for the large mass. I'll say this is y equals 0. And I suppose I could remind you real quick about the geometry here. Here's the string length. The ball is swung from here to here. And we can look at this right triangle here. If this is theta, this distance right here is L. This distance, the adjacent side of this triangle, would be the hypotenuse, also L, times the cosine of theta. If I subtract those two, if I take L minus L cos theta, I will get this final height here, the height at time 2. We've seen that before. So let me label these masses. I'll go with mass A and mass B because that is consistent with the form of the equations that I wrote down earlier. The one that's not moving is the one that I tend to call mass B. Now, right now, I'm applying conservation of energy just to this guy. Mass A has already bounced off to the left, and presumably it would keep its kinetic energy. We don't care about that. We're just looking at how the kinetic energy of mass B is transformed into the potential energy of mass B. So I would say K of mass B at time 2 plus potential energy of mass B at time 2 is the kinetic energy of mass B at time 1 plus the potential energy of mass B at time 1. Now when it gets to the top, it stops for a moment. Don't have to worry about that term. And at the bottom, its y-coordinate, or the y-coordinate of the center of mass, is 0. And so when I plug that into mgy for gravity energy, I would just get 0. So I'm really going to say that mgy at 2 would be 1/2 mb vb1 squared. This is the kinetic energy of mass B at time 1. That's right after the collision, but before the upward swing. I'm sorry about this bleed through the ink here. Here's where we plug in that expression for the y-coordinate at the top. I will say, and notice how the MB's canceled, don't even need them. GL, I've factored out the L, 1 minus cos theta max is equal to 1/2 VB1 squared. And what are we even solving for? Well, ultimately, we're going to relate this velocity to this velocity. So I need to solve this for VB1. VB1 is the square root of 2GL 1 minus cos theta max. Okay, so we've applied the conservation of energy because we argued that there's no non-conservative work being done. Now we go back and look at the collision between these two. And that's just a straight up application of those formulas that we just developed. Well, I didn't really do the algebra, remember, I just quoted the result. So here I'll say for the one-dimensional elastic isolated, meaning no outside forces, isolated collision with velocity of mass 1, I'll say initial. I don't want to say 1 because it's a little, this might confuse you. For this collision, my before and after are times 0 and 1. But when I wrote those formulas down, I think I said times 1 and 2. So you have to reset your use of notation, at least for this particular problem, the way I set it up. Okay, now you may be wondering, are you sure this is isolated? Because while these two are colliding, I see a string here, and that string is pulling on the mass. So there is an outside force. Plus there's gravity. Well, that's true, but the tension force is vertical, and so is gravity. So number one, vertical forces have no effect on horizontal momentum. And during the time that they're colliding, they're still moving horizontally. So there's that, but also kinetic energy should still be conserved because this tension is pulling up while the ball begins to move that way. In other words, the tension cannot do work, so it's not changing the energy. Okay, so it's still an example of the special collision that we're talking about. Okay, I'll just quote the results that we already wrote down. The velocity of mass A after the collision, well, after is now the number 1. That would be MA minus MB over the sum times the velocity of mass A before, and that right now, before is a times 0. So I've adapted the subscripts slightly. Also, the velocity of mass B after the collision is the velocity, excuse me, it's 2ma over the sum times the velocity of mass A originally. Now in this problem, which quantities do we have and which are we solving for? We know the masses, those were given, so those ratios are easy to compute. We've got a 20 and a 100. But amongst these three quantities, initial for A and final for A and B, which do we actually know? Well, remember, they told us what theta max was, which means since we also know L, we do know what this was. We know VB1. This is the number that's known. So I think what we could do is solve this equation for VA naught, plug that in there, and then we'll know what VA1 is. Great. So take this. This implies that VA naught is MA plus MB over 2MA times VB1. Okay. And let's substitute this entire expression for VA naught in here. Put that in there. VA1. That's the velocity of that's the velocity of the little ball as it bounces backwards. Here's where I substitute. Okay, so if we know the velocity of the larger ball, the one that was hanging there after the collision, then we also know the velocity of the other ball after the collision. Now I'm looking at the problem here, and they actually don't even need this, so I did a little extra work. We're not being asked for this. We're only being asked for this quantity. So we can evaluate this now. This is how fast the little ball was moving on the way in, but that is what was just called V naught. Your book didn't label it VA naught. I'm the one who introduced the letter A to distinguish the mass, but VA0 is the same as what they call V naught. So let's solve. We've got 20 grams and 100 grams, so 20 minus 100 over 20 plus 100. I'm sorry, I'm looking at the wrong equation, aren't I? I should be doing this one right here. Okay, so that's 20 plus 100 over 2 times the 20 grams, so that's 40 times. And then here's where you would want to actually evaluate VB1. So let me do that real quick. We're told that the max angle is 50 degrees. Okay, so I'm going to say 1 minus 50 cosine. I hit equals first. Then I multiply by the 1 meter by 9.8 times 2, hit equals, take the square root. And it looks like this is how fast the massive ball, the 100 gram ball was going just as it started its upward swing. I'll round that to 2.65. So let me continue this right here. 20 plus 100 That's 120 over 40 times 2.65 meters per second. The zeros cancel. 12 over 4 is 3. I'll just multiply this by 3. Evidently, the ball was going 7.9 meters per second. This is a solid problem because you have to apply some of these principles repeatedly, ties a bunch of stuff together. I'm going to remind you in an email to review this problem, especially because your homework, I cannot believe I neglected this, but your homework does not actually include problems where you have to apply the equations that I just developed. I could have sworn that those were in the homework, and I don't see them. Okay, I'll follow up with an email.